So what are successive ionization energy? Let's say if you have an atom from group 2 that is magnesium. If you make the electronic configuration of magnesium, if you just show the electrons in the quantum shells, magnesium valence shell has 2 electrons and its second shell has 8 electrons and the first shell has 2 electrons. Now what is successive ionization energy? If you just start removing electron from this magnesium atom, so the first electron that you would gonna remove would be from the outermost shell, right? So the first electron that you are going to remove from the magnesium atom would be from the outermost shell. Its first shell has 2 electrons, second shell has 8 electrons, and the valence shell has 2 electrons. The first electron that you are going to remove would be from the outermost shell. So that would be your first electron to be removed. So the energy required to remove this electron would be called as first ionization energy of magnesium. And after removing this electron, when you have to remove the second electron from the magnesium atom, that would be your second ionization energy. Again, we won't just study about ionization energy for one magnesium atom, we would consider 1 mole of magnesium atom. So again, it would be energy required to remove 1 mole of electrons from 1 mole of magnesium atom to form 1 mole of magnesium ions. So what do you think? Which ionization energy would be greater, the first ionization energy or the second ionization energy? Second ionization energy of magnesium would be greater than its first ionization energy. First, just write the concept of successive ionization energies. What are successive ionization energies? If you remove electron from any atom, one after the other, removing electrons from the atom, one after the other. Right? So second ionization energy of magnesium would be greater than its first ionization energy. It means in order to remove the second electron from the magnesium atom, you would require more amount of heat energy. And the reason is that because once you have removed the first electron, now the remaining electrons of magnesium are attracted by the greater nuclear pull. Because initially 12 protons of magnesium were holding 12 electrons in its shells. 12 protons were holding 12 electrons, right? But once you have removed one electron, now the number of protons are same, but the number of electrons have decreased by one. Now the remaining 11 electrons are still being held by 12 protons. So now the force of attraction on the remaining electrons would be greater, right? Second ionization energy would be greater than the first one, and the third ionization energy would be greater than the second one. All if you just keep removing electron, every ionization energy, every successive ionization energy would be greater than its preceding ionization energy. I mean, first would be the smallest, the second would be larger, third would be more larger, fourth would even be more larger. So the successive ionization energies basically increases as you start removing the electrons one after the other from each atom. Because once you keep removing the electron, what happens? Number of electron decreases, but number of protons stays same. So effective nuclear attraction or effective nuclear charge increases. So it becomes difficult to remove the remaining electrons. Getting my point? Okay. Now, if you're going to compare the third ionization energy of magnesium with its first ionization energy, which ionization energy you going to think would be more greater? Third ionization energy or second ionization energy? Obviously, third ionization energy is more greater than the second ionization energy. Let me just see if we have a pre-written notes of it. So second ionization energy would be greater than first ionization energy, and the reason being that once electron is removed, the remaining electrons experiences greater effective nuclear charge. So successive ionization energies always increases. But if we gonna compare third ionization energy with second ionization energy, this is our first ionization energy, then it should be greater. Second ionization energy is greater. But if we're gonna compare third ionization energy from second ionization energy, third ionization energy is actually shows a big jump. Third ionization, the increment between first and second ionization energy was small, but the increment between second and third ionization energy is very large. And the reason being because now the third electron for the magnesium atom that you have to remove is in the inner shell. If it is in the inner shell, it means it requires greater amount of nuclear pull. It requires a lot amount of heat energy to be removed because first of all, it is more closer to the nucleus. Secondly, it experiences lesser shielding effect. Because when you were removing the first and the second electron, they were present in the third shell, which experiences shielding from the two inner shell electrons. However, once you have removed both of these electrons from the valence shell, now the third electron that you're going to remove is in the inner shell. It is in the third shell, right? So this electron of the third shell is actually more closer to the nucleus. Secondly, and the important reason is it experiences lesser shielding effect. So if any electron experiences a lesser shielding effect, it means it becomes more difficult to remove it. Let me show you the values of successive ionization energy. It would give you a clearer picture. We're talking about magnesium. If you see the successive ionization energy values for magnesium, these ionization energies are for magnesium. Now, if you just compare their values, both of these, all the successive ionization energies always increases, right? There's no doubt about it. If you see for magnesium atom, this first ionization energy has a value of 736 kilojoules per mole. But as you see, the second ionization energy is greater than the first ionization energy. But the increase in between second and first ionization energy is 714 kilojoule per mole. But if you see the increment between third and fourth ionization energy, it is very large. This is a big jump. And the reason behind is because now the third electron that has to be removed is in the second shell or the inner shell, which experiences lesser shielding effect. So if they ask you why there is a big jump, let me rephrase the question. Why there is a big jump in the values of second and third ionization energies. And this is due to the third electron to be removed is in the inner shell, which experiences greater shielding effect. Hence, more energy is required to remove this electron. Oh, sorry, it experiences lesser shielding effect. I have written greater shielding effect. It experiences lesser shielding effect. Thank you, Rehan. Is it clear? Aisha, Rehan, Rida, Faik, and Sarah? Okay. Should we move on? Yes, I can wait, Rida. If you want to copy, I can wait. Done? Okay. Now, if we just see the values of first ionization energy of sodium atom, in the sodium atom, here we can see that our first ionization energy is 500. Sodium has one valence electron. Have you guys ever thought that a sodium atom has one valence electron, magnesium atom has two valence electrons? We cannot see the atom. However, we are so sure that this atom, this sodium atom or the magnesium atom or the aluminum atom, we even know their number of valence electrons. How come? We got to know about their number of valence electrons or any number of electrons in any of the shell by using the values of ionization energies. Because if you just compare the values of successive ionization energies of sodium, once you have removed the first electron, the energy required to remove the first electron that you're going to remove from any atom would be in its outermost shell, right? It should be in the valence shell, because once you start removing the electron, you remove the electron from the highest energy orbital first. When you are adding the electrons to any atom, you start adding the electrons from the innermost shell. But when you start removing the electrons, you remove from the outermost shell, because outermost shell are at the highest energy level. So once you have removed the first electron or the electron in the outermost shell of the sodium atom or any other atom, so the energy required was 500 kilojoules per mole. But if you see the second ionization energy of sodium, it is showing a big jump. Just from 500, the value is 4600, because once we have removed the one electron from the sodium atom, now the second electron that need to be removed would be in the inner shell. So inner shell electrons experiences lesser shielding effect, and secondly, they are more closer to the nucleus. So obviously they would require a greater amount of energy to be removed. So the values of second ionization energy has a big jump if we're going to compare it with the first ionization energy. But once you have removed the electron from the second shell, now the third electron that you have to remove from the sodium atom. See, first electron, second electron, and now the third electron that you are going to remove from the sodium atom would again be in the same shell. So there won't be any big difference between the values of second and third ionization energy. Although third ionization energy should be greater than the second ionization energy, because once you just keep decreasing the electrons, the remaining energy required, the energy required to remove the remaining electron would always be greater. But there is not a very big jump between second and third ionization energy. It was 4600 and it has become 6900. Now, if you see the fourth electron, not there is an increase, but not a big jump, because the fourth electron is also in the second shell. If you just keep removing the electron one after the other, because all of these electrons that have been highlighted in the blue color, they are being removed from the same shell. But this second shell has 8 electrons. Once you have removed all these 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. Now, the next electron that you're going to remove would be again in the inner shell. Now, again, you have to change the shell. It means the next electron, that would be the 10th electron of magnesium atom that you have to remove, would be in the innermost shell. So what do you expect? What should be the difference between the values of 9th and 10th ionization energy? Would just be a small or normal increase, or would that be a very big increase? If you just compare the values of the 9th and 10th ionization energy, the value of 9th ionization energy is 28,900. But as you can see, the value of 10th ionization energy is 1,41,000. So there is a massive big jump in the ionization energies from 9th to 10th ionization energy. Why? Because now the 10th electron that you're going to remove is in the innermost shell. So the big jump between the ionization energies tells us that the number of shell has changed. So when the first big jump in the sodium atom was from the first and second ionization energy, and this proves that once you have removed the first electron, the second electron that you're going to remove would be in the inner shell. This tells you that the valence shell of sodium must have only one electron. See, let me give you an example of any other atom, but instead of showing you the table values, how about if we just draw the graph of these values? If you consider the graph on the left graph, this says on x-axis the number of electrons removed. On the y-axis it says ionization energies. But this graph is not actually very clear. The reason being, some of the ionization energies are very close to each other. If you see the difference between the first and second ionization energy, you would say they are nearly constant. However, we have just established that successive ionization energy always increases. Maybe not with a big jump, but they always increases. So if you see this graph, the values of ionization energies does not show a big increment. The reason being because these values are very close. Because whenever we are plotting the graph, we have to relate all of these values. So how can we just make a graph that should be more prominent, that would be more visible or more prominent? Instead of taking the values of ionization energies directly, what we do is we have a mathematical tool which is known as logarithm. So we use log of ionization energies. Log is a key that you can easily find in your calculators. If you see your calculators on the right hand side, the second column from the right, you can see the value log. Log is basically the tool that makes smaller values larger or larger values smaller. Have you guys ever heard of log? If you guys have mathematics, then you would going to study logarithm. If you guys are not a mathematics student, then you would be studying about logs in A2 chemistry as well as in A2 physics. But for now, you just have to realize, if you see the graph and if you see anything written like log, this is the mathematical tool. And log of ionization energy is just used to make a graph more prominent, to make the values separated from each other. And you do not have to know how log operates. You just have to realize that this y-axis of ionization energy. That's it. Now if you see this graph, now here we can see there is a difference between the first and second ionization energy. When we were just making this graph directly with the ionization energy values, there is a difference between first and second ionization energy, but we couldn't see it. But with the logarithm, we can make it make the values separated from each other. So the first ionization energy has a value, whatever it is. The second ionization energy has a greater value. But if you just see the third ionization energy, its value is much greater as compared to first and second ionization energy. This is a big jump. So big jump comes after 2 electrons. Once you have removed 2 electrons from this particular atom, there is a big jump. It means the valence shell of this particular atom must have how many electrons? Once you have removed 2 electrons, there comes a big jump. It means the third electron that you are going to remove should be in the inner shell. So the valence shell of this atom must have 2 electrons. So it must be from group 2. And that's how we got to know how atoms have how many electrons or valence electrons are present in any particular atom. So a magnesium atom is from group 2, and we can prove through these ionization energies that a magnesium atom must have 2 valence electrons. So the first and the second ionization energy is basically for the electrons that are present in the valence shell. Once you have removed these 2 electrons, now the third electron that you are going to remove would be in the inner shell. And this inner shell has 8 electrons. So there would be an increase in between these ionization energies, but all of these ionization energies would not show a big jump because they are being removed from the same shell and there is no change in the shielding effect. However, when you are going to remove the electron from the innermost shell, see again, after once you have removed further 8 electrons from the second shell, now you have to move to the inner shell. So again, there is a big jump between the ionization energies. So this suggests that now again the shell has changed. So the outermost shell would be the shell where you have removed the first electron. So the outermost shell has 2 electrons, which is the third shell of magnesium atom. You guys getting my point? Faik, Sarah, Aisha. Okay. So you should know these 2 answers. Why successive ionization energy increases? Because once we start removing the electrons, now the remaining electrons experiences greater effective nuclear charge. But why there is a big jump between successive ionization energies? Because big jump comes whenever we are trying to remove the electron from the inner shell. So if you're going to compare the ionization energy of the electron from the outer shell and the ionization energy of the electron from the inner shell, there would always be a big difference because the inner shell electrons are more closer to the nucleus, and secondly, they experiences a lesser shielding effect. So it requires a lot amount of energy to remove that electron. If you see the ionization energies of oxygen, can you guys just identify where is a big jump in between which 2 ionization energies can you find a big jump in the oxygen atom? I'm asking you guys. 4th and 5th. Okay, 1 and 2. Sarah is saying 1 and 2. Rayan is saying 4th and 5th. And Sarah is saying 6th and 7th. And Faik is saying 7th and 7th. 6th and 7th. Okay. 6th and 7th. Obviously, oxygen is from group 16. Oxygen atom has 6 valence electrons. So it means once you have removed 6 electrons from the same shell, now the 7th electron that you are going to remove from the oxygen atom would be from the inner shell. See, oxygen atom has total of 8 electrons. Its valence shell has 6 electrons. 1, 2, 3, 4, 5, 6, and its first shell has 2 electrons. So if you're going to remove first electron it would be from the second shell, second electron, third electron, fourth electron. All of these electrons are being removed from the same shell. So they are all experiencing same shielding effect. However, there is a slight increase from first to second and second to third, and that is because once the remaining electrons that are left experiences a greater effective nuclear charge. But once you have removed sixth electron, the seventh electron that you're going to remove would be from the inner shell, which experiences, in fact, in case of oxygen, it does not experiences any shielding because there is no other shell beyond this shell. There are only two shells present. So this seventh ionization energy should be much greater as compared to sixth ionization energy. Even if you see the values and if you just get confused, you can always take the difference between the values of successive ionization energy. If you take the difference between first and second, you would get some value, second and third, fourth and third, fourth and fifth, fifth and sixth. If you see, the first ionization energy was 1310. Then it becomes 3300 something. Then it becomes 5000 something. Then it becomes 7000 something. Then it becomes 11,000. Then it becomes 13,000 something. But right after 13,000, there is no 16,000 or 18,000. There is directly 71,000. So don't you think it is a big jump? As if you see all the ionization energies up till sixth ionization energy, obviously there was a jump. But you have to relatively compare the ionization energies of that particular atom. You cannot compare the ionization energy values of oxygen and sodium. You cannot make your argument like this that in case of sodium, in first and second ionization energy, you were calling it a big jump. But if you see the first and second ionization energy of oxygen, then again, this could be called as a big jump. If you're going to compare it with sodium, then yes, you can say, oh, see, there is a big jump between second and third as well. Do not compare it with the values of the other atoms. Compare it with the values of its own successive ionization energies. In between these ionization energies, where you are finding the big jump. You cannot compare the values of successive ionization energies of the other atoms. Right? Sarah and Rayan, you got it now, bache? Okay, great. Tidy. Okay, the next topic that we have to study is isotopes. Can anyone of you define isotopes? What are isotopes? Yes, isotopes are the atoms of the same element with same number of protons but different number of neutrons. Atoms of the same element with same number of protons but different number of neutrons. Or alternatively, you can also talk about in terms of subatomic particles that they have same number of protons but different number of neutrons. Or you could have also said they have same atomic number but different nucleon number. Everyone knows what isotopes are. But let's say if you have a chlorine element has two isotopes. One with the mass number 35 and one with the mass number 37. Both have atomic number 17. Because if these two atoms have to be isotopes of each other, they must have same atomic number. It means they must be the atoms from the same element. But one of the isotopes have a mass number 35, one of the isotopes has a mass number 37. But from which isotope should we represent a chlorine element? In the periodic table, if you see, the atomic mass of chlorine given is not 35 or either 37. It is 35.5. So whenever we have to represent a chlorine element, we have to use at least one isotope, or we can just use one atom of any of the isotope. So it would be unfair if we just represent the chlorine element with any one of these isotopes. So instead of taking any one of these isotopes, what we do is we take the average masses of both of these isotopes. And how do you take average? It's simple. You have to see the percentage abundance or the relative abundance. Because if you just have a sample of 100 chlorine atoms, and if you just count from these 100 atoms, how many atoms are there with the mass number 35 and how many atoms are there with the mass number 37? So for chlorine, throughout the world, in our Earth's atmosphere, wherever we have found chlorine, we have found only two isotopes, one with the mass number 35 and one with the mass number 37. And in a ratio 3:1. That is, the isotope of chlorine with the mass number 35 is always 3 times greater as compared to the isotope with the mass number 37. No matter how much amount of sample we take from where we bring the chlorine. It can be any country of the world or any atmosphere around the earth. Wherever we have found chlorine, we have just found two isotopes. I'm not saying that in future we cannot find a third isotope of chlorine. Maybe we can, one day Elon Musk takes you to the Mars and from where they collect the chlorine element and there may be a third or even the fourth or the fifth isotope of chlorine. But up till now, we have found only two isotopes of chlorine. One with the mass number 35 and one with the mass number 37. And if we just start separating these isotopes, we find that out of 100 chlorine atoms, there are always 75 atoms are those with the mass number 35 and 25 atoms are those with the mass number 37. So if we just convert these into the percentages, 75% are the isotopes with the mass number 35 and 25% are the isotopes with the mass number 37. And these percentages are known as relative abundance or isotopic abundance. So instead of just representing a chlorine atom by one of these isotopes in the periodic table, we take the average. And we take the average on the basis of percentages. Like 75% of chlorine with the mass number 35. So it should be 75 over 100 into 35. And 25% of chlorine with the mass number 37. If we just take the average of these two values, we would get 35.5. And this average mass is basically given the name. Then now we cannot call it a nucleon number because we have taken the average of this nucleon number. So it is given the name as average relative atomic mass. Got it? I think you must have already studied that in grade 11. You did, right? Okay. Any questions so far? Okay. But the thing is, you cannot see an atom, right? How you came up to the conclusion that a chlorine element has two isotopes? Not just that, you also know their mass number. That these two isotopes, one with the mass number 35 and one with the mass number 37. And even more than that, you know what is the percentage of the isotope with the mass number 35 and what is the percentage of isotope with the mass number 37. I've been saying it hypothetically that if you have 100 chlorine atoms, if you just start separating these chlorine atoms, obviously you cannot just pick one chlorine atom because it is so tiny, you cannot have any provision to pick one chlorine atom or one chlorine isotope. So how you came up to the conclusion that there are two isotopes, one with the mass number 35 and one with the mass number 37. Not just that, you also know their relative abundances or percentage abundances. So how we actually got to know about this, it is due to one of the machines that we use in our laboratories, not in just all the laboratories, but this is a very costly and very sophisticated machine. This is known as mass spectrometer. We call it a mass spectrometer. And how does a mass spectrometer work? The detailed working principle is not included in our specification, but we have to try to understand the raw concepts. How does a mass spectrometer works? Because let's say if we have to determine the isotopes of chlorine, chlorine element is available in the form of chlorine gas in room temperature or in natural state. We cannot just find chlorine in the solid state. We would always find chlorine as a Cl2 gas because chlorine always exists in the diatomic form. So what we do is mass spectrometer. In mass spectrometer, we put this chlorine gas. And how does a mass spectrometer work? A mass spectrometer has 4 stages of operations. Let me show you the diagram, diagrammatic view of mass spectrometer. First, we have to perform the ionization of any element or any sample of any element of which we are trying to find the isotopes. Then, once they have been ionized, we accelerate those ions. Ionized means they have to be given a positive charge, and then we move these ions with a very high speeds. And once these ions start moving with a very high speed, we pass them through an electric or magnetic field so they can be deflected. Once they are deflected, they can be detected. That how many isotopes are there and what is the percentage of each isotope. Let me just try to explain it to you with one of the examples that we have for chlorine. See, a chlorine molecule may have, let's say initially we didn't know that a chlorine molecule, a chlorine element has 2 isotopes. So what we were going to do is, if we have a chlorine molecule, what are the possibilities in between these chlorine molecules? But now for the sake of making the concept, let me tell you there are 2 isotopes of chlorine, one with the mass number 35 and one with the mass number 37. But if we see just a chlorine molecule, there is a possibility that both of these atoms in this particular molecule must have a mass number 35. What can be the other possibility? The other possibility is one of the isotope has a mass number 35 and the other isotope has a mass number 37. Is there any other possibility? Yes. The third one is maybe both of the chlorine atoms in this particular molecule must have mass number 37. Now you just tell me, is there any other possibility? Because there are only 2 isotopes of chlorine. They may be of both 35-35, 35-37 or 37-37. Do you think, is there any other combination in a chlorine molecule with these isotopes, with only 2 isotopes? No, right? 3 combinations are possible. Now what happens in a mass spectrometer? Every sample that we enter into a mass spectrometer is actually bombarded with fast moving electrons. Now what these electrons do to the molecule or any sample that is present in the mass spectrometer, when these electrons, they collide with the molecule. So they may collide anywhere. They may collide with the electrons of the shed pair. They may collide with the electrons that are present in the lone pair, in the valence shell as a lone pair. So when these electrons or the fast moving electrons collide with these electrons, they may hit these electrons and knock them out from their shells. And when they knock them out, obviously the bond between these 2 chlorine atoms would break. And maybe there is a possibility that one of the chlorine atom loses one of its electrons. So it will get a charge of +1. So basically what we want to do in the mass spectrometer is that first we have to make anything that is being tested a positively charged ion. It may be any atom or it may be any molecule. If let's say in case of chlorine was a molecule. So when the fast moving electron collides with a chlorine molecule, some of the chlorine molecules have their covalent bond broken and we get chlorine positively charged ion. So how many type of chlorine positive charged ion can be formed? We can have two types of chlorine positively charged ion, one with the mass number 35 and one with the mass number 37, right? Now what happens? After ionization, when these ions are accelerated, they are accelerated so that these ions start moving very high at a high speed. How can you accelerate these ions? If you just recall CRO from your O-level physics, we used to have a cylindrical anode, a cylindrical cathode, because these cylindrical anode actually tries to repel these positively charged ions from all the direction. So instead of these positive ions going in one direction, they just move in a straight line. No, that's not electrolysis. I was saying if you have studied cathode ray oscilloscope back in grade 11, I don't know if it is there in the physics syllabus or not, but we just have to move these positively charged ions at a very high speed, right? And once they start moving at a very high speed, what we do with them is we deflect these positively charged ions. This process is known as deflection. And how can we deflect these positively charged ions? We can pass them through an electric field. Let's say if we have an electric field set up by two plates, one is positively charged, which is kept at the bottom, and one is negatively charged, which is kept at the, positively charged place is at the top and the negatively charged place is at the bottom. When these charged particles, like chlorine, I'm talking about these charged particles, chlorine 35 and chlorine 37. When these charged particles, when they're gonna pass through the electric field, initially they were like together in a form of beam, but as they passes through the electric field, they will be deflected by the electric field. And when they're going to deflect by the electric field, one of the particle will deflect at a larger angle and the other particle may deflect at a smaller angle. So if you just see their angles of deflection, we call these angles as angle of deflection. From the horizontal line, if you see their angle of deflection, one particle has a larger angle of deflection. The other particle has a smaller angle of deflection. So on the basis of difference in their angle of deflection, they have been separated. Now, why they have different angle of deflection? Because their angle of deflection depends upon two factors. Angle of deflection is directly proportional to the charge of particles, but inversely proportional to the mass of particles. If two particles have a greater charge, they will experience the greater electric force while passing through the electric field. But if their mass is heavy, they won't be deflected at a larger angles. If something is heavy, it is difficult to deflect them at larger angles. Do you just remember when you used to pass protons, neutrons, and electrons through an electric field? Protons are deflected at a smaller angles, right? Electrons are deflected at a larger angles. And why is that so? Because protons and electrons both have equal magnitude of charge. Proton is positively charged and electron is negatively charged. That's why they are being deflected in the opposite direction. But the lighter one, that is electron, is deflected at a larger angle because it is lighter. Because both of these charged particles, protons and electrons, they are experiencing the force, or the magnitude of force is basically dependent over their value of charge. They both have equal charge. If they both have equal charge, they're going to experience the same amount of force in the electric field. However, the lighter particle, when going to experience the same amount of force, it will be deflected at a larger angle. Same goes with these two chlorine isotopes. They both have positive one charge. And when they passes through the same electric field, they experiences the same value of force. And when they experience the same value of force, the particle which is heavier will be deflected at a shorter angle. The particle which is lighter will be deflected at a larger angle. So chlorine 37 is deflected at a smaller angle, whereas chlorine 35 is deflected at a larger angle. So how we came up to the conclusion that there are only two isotopes of chlorine? Because when these particles are deflected, they are hit on a screen which is known as detector. When the detector detects the signal, detector is now detecting two sorts of signals. One particles are there coming and colliding at the bottom, the other particles are coming and colliding at the top. So the detector is getting two signals, and two of these signals are at a different value, right? Chlorine with the mass number 35 is more downwards, whereas the chlorine with the mass number 37. And we can also count the proportion of their signals. For example, if total 100 signals were obtained at the detector, out of those 100 signals, the signal that is at the below at the detector was 75 times greater. If let's say the total number of signals detected were 100 and 75 signals were due to this peak or due to this particle, and 25 signals were due to this particle. So we can take the percentage, like 75% of 100 into 100 would give you 75%. So that's how we came up to the conclusion that the chlorine has two isotopes. One of the isotope has a mass number 35, the other isotope has a mass number 37. And the relative abundances or the percentage abundances can be found out by the number of signals that have been detected on the detector. If the chlorine 35 is getting greater number of signals, it means it has a greater percentage abundance. And how did we actually calculate their mass number? And the calculation of their mass number, obviously we are not going to study in chemistry. That would require some physics calculation, and that you would going to study in A2 level. It's not part of the specification. In fact, whatever we are discussing right now, we are just going slightly beyond the syllabus. In order to just to get an idea, we have gone not completely beyond the syllabus. You should have the working idea of mass spectrometer, that the first step is ionization, second step is acceleration, the third step is deflection, and the last step is detection. You should know the names of these processes. Otherwise, knowing all these like angle of deflection, yes, you are supposed to know that angle of deflection is directly proportional to charge. Whenever a particle has a greater charge, its angle of deflection would be greater. Whenever a particle has a greater mass, its angle of deflection would be smaller, because a heavier particle will be deflected at a smaller angle, but a particle with a higher charge would be deflected at larger angle. Getting my point? The steps are ionization, acceleration, deflection, and detection. I have already attached this diagram. Let me show you this thing. The first step is you have to ionize, then you have to accelerate, then you have to deflect, and then you have to detect. This detailed diagram, you are not supposed to remember this. You just have to remember these steps: ionization, acceleration, deflection, and detection. You're not supposed to know what amplifier is, what a charge recorder is. Okay now? That's how a mass spectrometer determines number of isotopes and the mass of each isotope. Secondly, I was saying, how come we get the mass of these isotopes? There are some complex formula, but I'm hoping you guys must have a slight idea of it. Like, do you guys know about centripetal force? Have you ever heard of centripetal force? Oh yes, that's nice. If you have already heard of centripetal force, it means whenever any particle is deflected or anything is deflected, this circle or this curve is part of a circle. So we can use the formula for centripetal force. That is Fc is equals to mv square over r. I'm not sure if you have ever heard of this formula or not, but this is the formula for the centripetal force, and we can actually relate this formula with the electric force. And in this electric force, we have a mass as well as the charge. But again, I cannot just tell you these formulas because that would be way beyond our syllabus now. Okay. So the result of this mass spectrometer, you should be able to read the result of mass spectrometer. Result of mass spectrometer is in the form of a chart or a graph like this. On the y-axis, it gives relative abundance. In the x-axis, it gives mass to charge ratio. And if you can see, the signals that we were getting on the detector are shown as a peaks in the mass spectrum. This chart is known as mass spectrum. And we will write about this in coming class, that this is known as mass spectrum. And how many signals can you see from this mass spectrum? 1, 2, 3, 4, 5. And x-axis gives us mass to charge ratio. Charge of all the isotopes has to be positive 1. So whatever the mass to charge ratio is basically their masses. Because in place of charge, you will be putting +1. So mass to charge ratio is basically equals to the mass of all the isotopes. So if we can see 5 peaks, it means a zirconium element has 5 number of isotopes, with each with the mass number 90, 91, 92, 94, and 96. Not just that, we can even see the relative abundances or the percentage of these isotopes from the y-axis. So we know the percentage, we know the mass number of every isotope, we know the total number of isotopes. Then we can just take the average mass of zirconium by multiplying these percentages from their individual masses. Got it? Tomorrow's class, we will going to continue this mass spectrum and we will practice some questions. And then we will be done with our first topic. And then, of course, once done, we have to conduct a test of your first unit. And from the coming week, we will start our second unit. Now, things will get paced up. You have to do questions as well as you have to prepare for your test as well. Got it? Anything you guys need to ask? Anything, any feedback or regarding anything like questions regarding lectures? Do you guys now have access to all the recorded lectures and class notes?